Hi friends, welcome to my chemistry class. I'm V. Ragasuma. Today I'm going to teach you about the crystal field splitting of the tetrahedral complexes. Previous session I have explained you about the crystal field theory, postulates and crystal field splitting of the octahedral complexes and the shapes and the orientation of the d orbitals in the metal complex were also explained for you. In this session, I'm going to explain about the crystal field splitting of the tetrahedral complexes. The splitting of the degenerate orbitals into different orbitals having different energies in presence of crystal field is called crystal field splitting. This crystal field splitting is very important for the crystal field theory. Now we'll see the crystal field splitting of the tetrahedral complexes and crystal field splitting of the square planar complexes. Now we'll see the crystal field splitting in the tetrahedral complexes. Once if you tell about the tetrahedral complexes, we just remember Ml4 formula. Tetrahedral complex means Ml4 formula. So the ligands are 4, the coordination number is 4. Such type of complexes are called as the tetrahedral complexes. Now in the tetrahedral complexes, the orientation of the ligands will see. So it is just a bit difficult to imagine, but seeing the diagram, you can understand. The splitting is slight difficult. It is just quite reverse. The splitting of the d orbital in the tetrahedral complexes is quite reverse to that of octahedral complexes. The four corners of the tetrahedron occupy four corners out of 8 corners of the cube. You can see the cube here. There are 8 corners. In that 8 corners, the ligands are occupying the 4 corners. Okay, the splitting of the d orbitals in the tetrahedral complex. It is very easy to understand the splitting pattern if the geometry is understood. So just assume a cube. In this cube, you're having 8 corners. 1, 2, 3, 4, and here 1, 2, 3, 4. 4 plus 4, 8. In that, you're having only 4 corners. You're having the ligands. These ligands will be approaching the central metal atom. So these are approaching in between the axis, x-axis, y-axis and z-axis. So the ligands are approaching in between the axis, coordinate axis x, y, z. You can see the ligands. A cube is there, 4 corners the ligands are there. One corner you're having the ligand which is in between the x, the y and z-axis. Another ligand is between x and y. Another ligand, it is between the x and y. Again, y and z. So all the 4 ligands will be approaching in between the coordinate axis. So you just remember the d orbitals. Previously I have explained you the d orbitals. There are 5 sets of degenerate d orbitals. One is T2G set and the other one is EG set. T2G set of orbitals are dxy, dyz, dzx. EG set of orbitals are dx square, y square, dz square. So T2G set of the orbitals are in between the electron clouds and the lobes of the electron clouds and the lobes of the d orbitals. T2G set of d orbitals are in between the coordinate axis. They're in between the coordinate axis. While coming to the dx square, y square and dz square, EG set of orbitals are along the coordinate axis. So I hope you are able to understand 5d orbitals, T2g set, EG set. In that, T2g set is in between the coordinate axis, whereas EG set is along the coordinate axis. So when the ligands are approaching in between the coordinate axis, T2g set will experience more repulsion and gain more energy, whereas EG set of orbitals are along the axis. So there is no ligand along the axis. Therefore, they experience less repulsion and less energy is gained. Now, as the ligands are approaching, these will undergo splitting, crystal field splitting. Okay, so now we'll see. Let us examine d orbitals, how they are experiencing. So as the ligand approaches the central metal atom, d orbitals of the metal oriented in between the axis are much more under the repulsion by the orbitals of ligands than the d orbitals oriented along the axis. So therefore, here the T2g set energy increases. T2g set energy increases. The energy of the EG orbital decreases. In this way, the 5 degenerate d orbitals split into 2 groups due to difference in energy. The energy difference between these two group of d orbitals is denoted by delta T. T is the tetrahedron. The energy of the EG group of d orbitals is 0.6. So we'll see the splitting and then we'll see the energy, how it's getting split. So in the tetrahedral complexes, I have told you the coordination number is 4. 4 ligands approach metal ion. In between the 4 ligands, I've told you cube, 8 corners, only 4 corners you're having the ligands. And from 4 corners, they approach the central metal ion. In between the axis, the energy of the T2g orbitals. So they are 4 ligands are approaching in between the axis, coordinate axis x, y, z. So the in between orbitals are T2g orbitals, dxy, dyz, dzx. The energy of the T2g orbitals, which are oriented in between the axis, increases. Energy of these orbitals increases due to more repulsions. Energy of the EG orbitals oriented along the axis decreases because they experience less repulsion. The energy difference between T2g orbital and EG orbital is known as crystal field splitting. Here you can see the diagram. D orbitals, they're having the same energy, 5 orbitals. As the ligand is approaching the d orbitals, the energy has increased. Still they are in the degenerate state, same energy state. Previously, energy is less. As the ligand is approaching, the energy, as the ligands are approaching, the energy of the orbitals increase, but still they are in the degenerate state. And as the ligands have approached to the center of the ligand, I have explained here, ligands are approaching nearer the metal atom. So the d orbitals in between the metal, the energy is increased. As these have approached very closer, the d orbitals experience difference in energy and repulsions. So since these are in between, the ligands are in between the coordinate axis, the in between d orbitals, that is T2g set of orbitals, that is dxy, dyz, dzx, experience more repulsion, gain more energy, and they undergo splitting. The orbitals along the axis, EG set, experiences less repulsion, less energy is gained. So they get stabilized. And the T2G set get destabilized. So they get more energy. Okay, here we'll see the splitting. D orbitals of the free metal ion in the degenerate state. As the ligand approaching, energy increase, still in degenerate state. As the ligands have approached still closer, they have got split into two types. One is T2G set and the EG set. T2G set of orbitals dxy, dyz, dzx. Previous session, if you see the previous session, you can clearly understand the d orbitals, shapes and orientation. Spatial orientation you can see. So dxy, dyz, dzx. These are in between the coordinate axis. Ligands are coming in between the coordinate axis. So these experience more repulsion, gain more energy, and they get split out. Here you can see the energy. When compared to this degenerate d orbitals, the energy of T2G set increased due to more repulsion, and energy of the EG set decreased due to less repulsion. So these have come down and these have gone up. In the octahedral, it is quite reverse. Orbitals, 6 ligands are approaching along the axis. Along the axis. So EG set has come up and T2G has come down. So tetrahedral is quite reverse to octahedral. In octahedral, ligands approached along the axis. So T2G has come down, EG has gone up. In the tetrahedral, it is reversed to that of octahedral. Ligands have approached in between the coordinate axis, x, y, z. So the ligands in between the coordinate axis are the T2G, experienced more repulsion, more energy. Therefore, the splitting has taken place. This is called crystal field splitting. This is called crystal field splitting. This is state 1, this is state 2, and this is state 3. State 1, degenerate orbitals of the free metal ion. State 2, degenerate d orbitals in higher energy level. State 3 is splitting in the tetrahedral complex. Electron that enters in the EG set gets stabilized by 0.6 delta T. This is delta T. That is the energy difference between T2G set and EG set. Delta indicates the energy difference for this tetrahedral complex. T indicates the tetrahedral. So electron that is entering the EG set of the orbital stabilizes the complex ion by 0.6 T. The electron entering the T2G set of the orbital is destabilizing. It destabilizes the complex ion. So whatever electron enters here destabilizes the complex ion. Whatever electron enters the EG set stabilizes the complex ion. Whatever enters here stabilizes. Electron that is entering into EG set will stabilize the complex ion. This will destabilize the complex ion. Okay, so electron entering into the EG set, the down orbital, stabilizes the complex ion by 0.6 T. And the electron entering into the T2G orbital destabilizes by 0.4 delta T. Okay, so you have understood the tetrahedral splitting. Now we'll see the crystal field splitting in square planar complexes. In the square planar complexes, you are having in the square planar complexes, you are having 4 ligands. There the minus charge indicates the ligands. -4 indicates the ligands. These are coming along the axis. These are also coming along the axis. Previously, what we have seen? Tetrahedral, Ml4, Square planar is also Ml4. M, here it is N plus. Here is the metal ion. These are the ligands. These are the ligands. Okay, minus charge is the ligands and the plus is the metal ion. For the central metal ion, Ml4, same like tetrahedral complex only. These are Ml4, 4 ligands, coordination number is 4. But there the 4 ligands approached in between the axis. But here the 4 ligands are approaching along the axis. That is only x coordinate axis and y coordinate axis. Along the x coordinate axis, 2 ligands are approaching. Along the y coordinate axis, 2 ligands are approaching. Along the z, there is no ligand. Remember, okay? Along the z axis, there is no ligand. There are 4 ligands, coordination number 4, 4 ligands, 2 approaching towards the x axis and 2 approaching along the y axis. 2 approaching along the y axis. Now, how the splitting pattern? It is quite different to that of octahedral and it is quite different to that of tetrahedral. So it's a different case, square planar. Now we'll see how the splitting will takes place. In square planar complexes, in the square planar complexes, you are having 4 ligands approaching in the xy plane. The diagram I've shown. The ligands are absent in the z-axis. D orbitals in the xy plane are more repelled. Okay? It is not the T2G set, it is not the EG set. Yeah, the division is the same. The division is the same, but the xy plane orbitals are more repelled. They are experiencing more repulsion than the orbitals in the x coordinate axis. Okay, so the d orbitals in the xy plane, just like octahedral, you can see, same like octahedral. Octahedral, you are having 6 ligands along axis. Here you are having 4 ligands along axis, but there are 6 ligands in the 3 coordinate axis. Here 4 ligands in the 2 coordinate axis. In the octahedral, x 2 ligands, y plane 2 ligands, z plane 2 ligands. But in the square planar, the ligands are in the 2 ligands in the x coordinate axis, 2 ligands in the y coordinate axis, and there are no ligands for the z plane. Okay, so therefore d orbital in the xy plane are more repelled to greater extent than that of octahedral complexes. Energy of the d orbital in xy plane. Xy plane, you're having dx square y square and dxy. So this orbital dx square y square orbital is EG set of orbital. dxy is T2G set of orbital. Okay, so one orbital of the EG set and one orbital of the T2G set. They are experiencing more repulsion and energy is increased. Okay, so delta SP, it is a colored delta SP. It is nothing but crystal field splitting energy in the square planar complexes. Now we'll see how the splitting pattern takes place. Once if you see the splitting pattern, now we have learnt previously d orbital splitting in the octahedral complexes. Okay, now the d orbital splitting in the square planar complexes we'll see. So by removing 2 vertical oriented ligands from that of octahedral, 2 ligands are removed. We get a square planar complex. By removing 2 vertical, that is z-axis, oriented ligands from the octahedral complex, we get square planar complex. If we consider xy plane as a square planar complex in that octahedral, we get square planar complex by removing the ligands present on the x-axis. Previously diagram I have shown. By removing away the 2 ligands present on the x-axis, the dz square oriented along the z-axis is completely free from repulsion. by the ligand orbitals. In the similar way, dxz and dyz. Okay, dxz, dyz. Here, dz square, dxy and yz. Okay, orbitals having the z-axis orientation, they get reduced here. This orbital, these two orbitals. No ligands along the x, therefore dz square, dxz, dyz. They don't have x z-axis orientation. Reduce their repulsion by the ligand orbitals to some extent. The energy of these orbitals is reduced differently. It is reduced differently. The energy of the dz square is highly reduced since the orbital is completely free from repulsion. It is completely free from repulsion. Okay, degenerate orbitals, they have splitted into previously degenerate, again the energy increased, again they have splitted into T2G and EG due to difference in energy. Again in the EG, x square plane there are ligands, so more energy, more repulsion. Z square there is no ligand, less energy, more they are getting stabilized. The energy is decreased, less repulsion, less energy. In T2G set, their XY is experiencing more repulsion and XZ and YZ are experiencing less repulsion. Thereon, the splitting will not stop here. The difference will not stop here. Still, they undergo repulsion. They undergo repulsion, they undergo splitting. Again, dx square, energy is still increased. Z square, energy is almost reduced. And xy, energy is increased. Still the ligands are in the xy plane. Now, xz and yz, the energy is still decreased. So this is the energy order and the repulsion order. Very less repulsion experienced is and energy is for xz and yz, z square, and then xy, little more energy, very less energy, stabilized, less repulsion, less energy, stabilized, less energy, less repulsion, less energy, somewhat stability. XY plane, a bit more energy, more repulsion. Here, more energy, still higher energy and high repulsion you can experience. Okay, so you can see when compared to the octahedral, the energy difference also you can see. So A and G, they are indicated these orbitals. Here, the orientation, according to the orientation there, the splitting. Okay, the energy of the d orbitals reduced very differently in the square planar complex. Energy of dz square is highly reduced since the orbital is completely free from, it is completely free from, yeah, the energy, it is complete, see the energy of the dz square orbital reduced since the orbital is completely free from the repulsion of the, by the ligand orbitals. Dxz and dyz orbitals are oriented between the xz and yz axis. There will be small repulsion between these orbitals and the orbitals of the ligands present on the x and y axis. So therefore, decrease in the energy of these orbitals is much less than decrease in the dz square orbital. Okay, in the dz square orbital. The energy of the dx square y square oriented on the xy plane is very high since these orbitals undergo high repulsion by the orbitals of the ligands present on the xy axis. The dxy, which is oriented between, is under less repulsion. It is under less repulsion by the ligands and the energy is little higher. The crystal field splitting is shown by delta Sp. The splitting crystal field splitting energy is shown by delta Sp. Okay. So the crystal field splitting energy delta Sp is more than delta O. Crystal field splitting delta Sp is more than delta O. So it is related. Delta Sp is equal to 1.3 of delta O. Delta Sp is equal to 1.3 into delta O. So the crystal field splitting energy is 1.3 times more. It is 1.3 times more. Okay. So what is the definition for the crystal field stabilization energy? The crystal field, the energy gap between the T2G and EG orbitals arised because of the difference in electrostatic field exerted by the ligand on T2G and EG orbitals of metal ion is called crystal field stabilization energy. I am repeating crystal field stabilization energy. The energy gap between T2G and EG orbitals arised because of difference in electrostatic field exerted by the ligand on T2G and EG orbitals of the metal ion is called crystal field stabilization energy. Now, what is a strong field ligand? What is a weak field ligand? Strong field ligands are those which exert strong electrostatic field on central metal ion and have high splitting power They are called as a strong field ligands. Okay. Now I'm just explaining you about the ligands. The splitting of the square planar complex is explained. Now I'm just explaining you some terms. What is crystal field stabilization energy? I have explained. What is a strong field and what is a weak field complex? Strong ligands are those which exert strong electrostatic field on central metal atom, and the high splitting power will be there. Strong ligands, high splitting power. Strong ligands, more electrostatic field on the central metal atom, and high splitting power. Example: cyanide, carbon monoxide, nitrate. All these are the strong ligands. Now, what are the weak ligands? Weak ligands are those which exert weak electrostatic field on the central metal ion, and they have relatively low splitting power. Okay, weak ligands exert less electrostatic field on the metal and less splitting power. They are the weak field ligand. Weak field ligands, less electrostatic power, less splitting. Example: iodide, bromide, chloride, fluoride. See, if you see my previous sessions, you can understand clearly. Strong ligand, weak ligand, I have told. So strong ligand and weak ligand complexes I told. What is a low spin complex? What is a high spin complex? If the d orbitals of the penultimate shell are used in the bond formation, penultimate shell, if the d orbitals of the penultimate shell are used in the bond formation, in the hybridization, in the valence bond theory, we came to that. So what is a low spin complex? After the splitting, these are the terms which should be known. So if the d orbital of the penultimate shell are used in the bond formation, then the complex is inner orbital complex. If the n-1 d orbital is in the bond formation, n-1 d orbital is in the bond formation, then that is the inner orbital complex. They experience low spin. That is called as a spin paired complex. Generally, they are diamagnetic. Okay. So if my penultimate shell, if the d orbital of the penultimate shell, n-1 d orbital, is used in the bond formation for the complex, then that is the inner orbital complex, low spin complex, spin paired complex, diamagnetic complex. Now, coming to the next one, high spin complex. If the d orbital of the valence shell, that is nd orbital of the central metal ion, is used in the bond formation, hybridization, then the complex is known as outer orbital complex, or the high spin complex or spin free complex. I am repeating, high spin complex. If the d orbitals of the valence shell, nd orbital of the central metal ion is used in the bond formation, hybridization, Then the complex is known as outer orbital complex, high spin complex, spin free complex. They are paramagnetic in nature due to presence of more unpaired electrons. Due to presence of more unpaired electrons. Okay, so I have explained four basic concepts, five basic. What is after all this splitting? We have seen what is a crystal field stabilization energy, what is a strong field complex, what is a weak field complex, what is a low spin complex, what is a high spin complex. I have explained. Now let us look on to the merits of the crystal field theory. Merits of the crystal field theory. It is very simple, very useful for the quantitative approach. It is very simple and it is very useful for the quantitative approach. So what is a quantitative approach? Nothing but giving the empirical, semi-empirical numbers. Okay. So in that way, we have the advantage of the CFT. Okay, it's a simple one, and for empirical and semi-empirical numbers, it is having the quantitative approach. It predicts the variation of the magnetic moment with the temperature. Previously, no theory, even the valence bond theory, couldn't explain the magnetic moment change with temperature. It is able to give the magnetic property, but it couldn't explain the variation of the magnetic moment with the temperature. But CFT, it is able to explain the magnetic moment with the temperature. And not only that, the detailed magnetic properties of the complexes are also explained. The detailed magnetic properties of the complexes also explained. It is able to predict the stereochemical properties. The stereochemical properties as the orientation of the ligands around the central metal. How the property of a complex is changing. So we are able to predict the stereochemical properties using CFT. And next, it is able to give the kinetic and thermodynamic properties. How kinetic properties and thermodynamic properties with the temperature, how the properties are changing, and how the speed of the reactions, the complex compounds are undergoing reactions, what is the rate of the formation of a new complex, so how this kinetics can be studied using the CFT. We are able to explain the kinetic and thermodynamic properties. It treats the spectral problems, the color properties, the spectral problems using the DD transitions, how the transitions are going on. After absorbing energy, the D electron jumps into the another D electrons, another D orbital. Therefore, the DD transitions can give the color properties, spectral properties. Why a particular color is there for a particular complex can be explained using the CFT. So you have more advantages. Along with that, we are having always it is concentrating. See, all this session I have explained, previous session also CFT. CFT postulates I have explained, CFT splitting of the tetrahedral complexes, octahedral complexes, square planar complexes are explained. Everywhere I'm talking about the metal orbitals, but I'm not able to give you the explanation of the ligand orbitals. So the orbitals of the ligands are neglected in this theory. He just concentrated on the d orbitals of the central metal ion. The splitting of the central metal ion, d orbitals is explained. But he has ignored the ligand orbitals. He couldn't explain the charge transfer bands. So due to the charge transfer, the bands appear. How, why couldn't be explained. The ML bonds are not purely here. It's not printed. The ML bonds are not purely electrostatic for all complexes. They're not purely electrostatic for all complexes. Previously, I told you they're electrostatic, pure 100% ionic point charges, I've told you. But here now, the ML bonds are not purely electrostatic. They are not, most of the complexes are electrostatic, 100% ionic. But some of the complexes, ML bonds, are not electrostatic. They are not ionic for all complexes. So why they're not ionic, why they're not electrostatic couldn't be explained by the CFT. He has told 100% ionic, 100% electrostatic. But that's not true. 90% only they're 100, they're 90% only electrostatic, and only 90% are 100%. It's not 100%. Only 90% is ionic. Some of the exceptions are there. They couldn't be explained using the CFT. Only 90%. Most of them are ionic. Okay, we agree. But to some extent, they're not ionic. They're not electrostatic. That couldn't be explained. The steric effects are also not explained in the CFT. What is a steric effect? It is nothing but if the bulky ligand is attached to the central metal ion, what is the stability condition? What is the stability condition of the complex? Couldn't be explained. So if a bulky groups are attached, what is the condition of that complex? Stability of the complex is not explained in this CFT. Okay, in this crystal field here. Okay, so previous session, that is one session, and this session is the second session for the crystal field theory. So previous session, d orbitals shapes are explained, previous shapes and the spatial orientation of the d orbital around the central metal ion is explained, and the shapes after that, understanding the shapes of the d orbitals, I have given the postulates of the, I have explained you the postulates given in the crystal field theory by Beath and Van Vleck. Whatever is given by Beath and Van Vleck were explained, the postulates were explained. And later on, I have explained you the basic terms. What is a crystal field splitting? What is crystal field stabilization energy? What is a weak, what are the weak field ligands? What is a strong field complexes? Strong ligand field complexes, weak field ligand complexes, low spin complexes, high spin complexes. I have explained you. And later on, we have seen crystal field splitting of the octahedral complexes, along with the diagrams, how the ligands are arranged in the complexes, how they've approached, how the splitting takes place was explained. And in this session, the crystal field splitting of the tetrahedral complexes, how the ligands are arranged around central metal atom, how they are arranged around the central metal atom, and how the splitting takes place was explained for tetrahedral complexes. Similarly, for square planar complexes also, how the ligands are arranged and how the splitting has taken place was explained. Along with that, I have explained the merits and the demerits. I hope everybody have understood my session. Okay? Thank you for listening to my lecture of the crystal field theory.